So the last section we did, P.4, we talked about polynomials. But what we talked about is what happens when we combine them with either addition, subtraction, multiplication, or kind of with division. We didn't talk a lot about division, but we did talk about it in reference to radicals. What we're going to talk about in this section is taking something that's already been combined and in some way, shape, or form breaking it back apart. That's really what factoring is breaking things apart. So if a polynomial cannot be factored, if that's not a possibility, it cannot be broken apart, we actually say that the polynomial is prime, or prime's the shorter word, right? Prime, or irreducible over the integers. Okay. So we're going to start with a very basic factoring technique, which is just greatest common factors. So what greatest common factors does is it takes any number of terms, this one has 2 terms, and it asks what's the biggest thing that divides them both. It's almost like looking at fractions and reducing them. What number goes into the top, what number goes into the bottom? I'll divide them both by 2. Right? It's the same idea, except that we're not dividing them, we're just drawing it out in front. So on this one, we have 12x squared and 18x cubed, and we're going to deal with the numbers and the variables separately. So let's first look at the numbers. I have a 12 and I have an 18. What is the biggest number that will divide both 12 and 18? 6. Okay, so I'm dealt with the numbers now. We'll get to the rest of it next. But let's look at the variables first. I have x cubed in one of the terms, and I have x squared in the other term. So what is the biggest x with an exponent that I have? X squared. Okay, so I have x squared. So what I have next then, if I'm actually factoring, are what happens when I divide each of those by 6x squared. So I am, in my mind, dividing. I'm just not eliminating as I do the division. I'm writing the division piece in front. So when I take 12 and I divide it by 6, I get 2. So there's a 2 left here. And it was x squared, and I pulled the entire x squared out, so I don't have any more variable left. The entire thing divided out. Or you can think of it as the x squared divided by x squared is 1, and 1 times the 2 that's already there doesn't change the 2. My sign stays the same, and we'll do the next one the same way. It's an 18. So what is 18 divided by the 6? 3. But then I have x cubed, and I only pulled out an x squared, which means there's still a x. So I have negative 3x. And if you wanted to confirm that you did it correctly, besides the back of the book or something like that, you could multiply it back out to confirm it, right? Yeah, you could. So this would actually be what the multiplication or the factorization looked like if it simply asked you what is the greatest common factor, right? If that were your question, your greatest common factor would simply be x squared, 6x squared. Okay, so it depends on the directions. Do they say just find the greatest common factor, or do they say to factor it using that method? So different options. The next thing we're going to look at are some special formulas. The first one is one I mentioned just a moment ago when we talked about section P.4. So it's a difference, that's what the subtraction means, a difference of 2 pieces that are squared. So I have a squared minus b squared. All 3 of these have special formulas for factoring. The first one is usually one you guys have seen frequently enough that it sort of triggers and you remember it easily. The next 2, not so much. So the next 2 is probably one of those things you want to highlight as you're doing your notes or whatever to remind yourself that when you're doing your homework, as you get to a quiz, when you get to an exam, have somebody quiz you on that and make sure that you remember the formula, because I won't give it to you. It's something you can memorize. It's not that bad. So the first one, when I have a squared minus b squared, factors is a minus ba plus b. And you might remember from the last section, those are called conjugates, right? Yeah, a minus b and a plus b, in either order. It's nothing special about putting the a minus b in front. I could put it at the back. So let me tell you how I remember the formulas for the last 2. Perhaps it's helpful, maybe it's not, but at least it's something that you have as an option. They will each have a binomial term, and they will each have a trinomial term. Okay? So one of them is going to be just like the binomial. The other one's going to be long, and it's going to be a trinomial. The binomial term is going to look just like the original expression without the cubes. Okay? So it's going to be a minus b or a plus b, depending on which sign is in the middle. So this one's called a difference of cubes. This one's called a sum of cubes. The other term is going to be sort of what feels like it's missing. For example, what would I have to multiply a by to get a cubed? A squared. So I clearly need an a squared. And I clearly need, by the same token, a b squared. Make sense? Because otherwise there's no hope in me getting b cubed. There's no hope in me getting a cubed. The inside actually ends up being the multiplication of a and b. I should put this first. The b squared, they're both positive. The a squareds and the b squareds have to both be positive for this to work. This sign will actually be determined by this sign here. That's why I need the positives on the end and don't need another negative there. So I need the multiplication of the a and the b in the middle on either formula. And then it's just the opposite sign that I already used. This one's negative, so this one's positive. This one's positive, so this one's negative. So if you fear that you've memorized it and you just might slip out of your head really quick before you actually start working with it on a test, you might write it on the top of the test before you start, right? Or the quiz or whatever you're working with. But that's how I think about it because I see patterns. That's something that my mind does pretty well is to remember patterns of things. If that's not you and you have a better way to think about it, go for it. Okay, so you guys ready to try some with this and some other methods? Okay, these three are all one of those types of formulas. Okay? So the first one, which of the three is it? So the first one's called a difference of squares, the second one's called a difference of cubes, and the last one's called a sum of cubes. Which one of those three is the first one here, number 2? It is a difference of squares. The thing that you need to be careful of is recognizing what is being squared. For example, let me do the 16 first. The 16 is 4 squared. That's what's being squared. Make sense? So on the first one, it's not the 9t that's being squared. T is being squared. But what number squared would give me 9? It's 3. So it's 3t that's being squared, and it's 4 that's being squared. That is a common pitfall, is to forget that that's the 3, not the 9, that I need to be using. Once I've identified those pieces, it falls just very nicely in the formulas we had before. So this is the one that I'm using. At the moment. So I need the first term, which is 3t. Minus or plus, it doesn't matter the order. I'll go with what I've got, minus the 4. And then I need the 3t plus the 4. And again, if I wanted to confirm that I had done it correctly, I could multiply it back out to make sure. Any questions on that one?
So that's your final answer?
It is your final answer. Yes, ma'am. That is the final factored form. Three is kind of tricky, because it involves more than one thing that we've done today. It involves a common factor. We've got 8x to the 4th, and I have 27xy cubed. What do they have in common? The x. If I don't pull that x out, I'm probably spinning my wheels trying to figure out what to do next. But once I pull the x out, it makes things simpler. So we're going to pull the x out first, and I'm going to pull it out over here to just see what's left. So I have an 8. X to the 4th becomes x cubed. The 27 stays. The x has been pulled out, and then I have y cubed. So I will have an x pulled out in my answer here in a moment. After I have it in this form right here, I need to decide. Difference of squares, difference of cubes, or sum of cubes? It's a difference of cubes. Yes, it is. The difference of cubes looks, it's the second one on here, it looks like this. Let me just set it right there for the moment. So I need to figure out what is being cubed, much like the last problem, because it's not an 8, and it's not a 27. So what number would I have to cube to get 8? 2. So it's actually the 2 and the x that are being cubed. What's being cubed to give me 27? A 3, and then of course also the y. Now, do you have to write this down like this? No, you don't have to. If you can just see it and move on, then more power to you. That's great. But just don't forget that step and inadvertently use the 8 or the 27. So, the funny thing is on this one, or maybe not funny, but the thing that can catch you off guard when you're working with this formula with the cubes is that in a moment here, I'm going to have to square some things. So we do need to be a little bit careful when we get to that point. Now, the first piece is just each of those individual pieces that are being cubed and with whatever signs between them, in this case the negative sign. So I've got a 2x minus 3y. That's my binomial term. Here's the kicker on my trinomial term, is that I have the 2x now, but it's being squared, which means I don't have 2x squared, I actually have 4x squared. I'll put it in there in a second, but I have a 4x squared. In the middle I have the opposite sign, so that's addition. And then I need the two numbers and their coefficient, or in their corresponding variables multiplied. So I have a 2x and I have a 3y, right? Because I'm going to have to simplify this in a moment anyway, I'm just going to write them in for now, 2x and 3y. They had to be multiplied. And at the end, I have addition. It's always addition. And then I have my last one, which was 3y, that's now being squared. Now, you don't have to write all those pieces in there, but one way or another, you need to arrive at this point where we've actually got those pieces squared and multiplied, right? So 2x squared, like we mentioned before, is actually 4x squared. The 2x times the 3y would give me 6xy. And then I've got the 3y being squared, which gives me 9y squared. It's a little bit tempting, especially as we continue on here in a moment, to ask yourself if this piece that's in the parentheses at the end, this trinomial, is actually prime. We used that word earlier, right? Maybe it factors further. And the answer is it never will factor further. If it had the possibility of doing so, we wouldn't have it left right here in the formula. Like, it just wouldn't happen. So we don't have to worry about trying to see if it will now factor. It won't. We're done. Any questions on that one? Yes?
Why would you not do the x times the 2x minus
Because our goal is not to distribute it through, it's to break it apart. So right now it's in its most broken apart, most factored form, and that's what we're asked to do on this particular problem, is to factor it. The phrase that they'll use in your book probably most frequently is going to be factor completely. And that's what we wanted to leave it as, factored it completely. Okay, 4 is a little bit more straightforward, but it has a nuance that's a little bit funny. Can you tell which formula this is? It's a sum of cubes. Now, it looks a little bit funny because of that 1. But that's okay because 1 is 1 cubed. 1 is 1 squared. So it's kind of nice, actually. What's the other term that's being cubed? The 64, the z's cubed. So the z's being cubed. What's the number I need? You're close. That would be 8 squared. I need something cubed. It's 4. That's one that we don't always think about. 4 times 4 times 4 is actually 64. Yeah. So 64 cubed is 4 quantity cubed. So the 64 is 4. All right, so we're going to use the sum formula. The first piece of the sum formula is the binomial, where it matches our individual pieces. So 4z, same sign, and 1. So the next piece squares things. So I'm going to do it this time while we walk through instead of writing out all the pieces like I did last time. It's supposed to be the 4z here squared. But what's 4 squared? 16. So it's 16z squared. In the middle I have the opposite sign, so it's subtraction. And then I have my two pieces multiplied, but 4z times 1 is 4z. That's very friendly. And at the end, I have my 1 squared, which is also very friendly to give me a positive 1. It's always positive at the end. Okay, all good? Fabulous. All right, we're going to look at another type of factoring today. There's a couple more we're going to look at. The next one is called factoring by grouping. Factoring by grouping is when you have 4 terms. Remember, we didn't have anything specific to call that. 3 terms is trinomial, but 4 terms doesn't have a name, anything beyond just polynomial. So you'll notice anytime we use factoring by grouping, we're doing 4 terms. Anytime you see 4 terms, that's sort of the natural inclination, is probably going to factor by grouping. Generally speaking, the groupings don't really matter. Sometimes you group them together and it's not going to work, and then you're like, okay, well that didn't work, now I got to try something else. So when I'm working with factoring by grouping, what I tend to do first is to just put them in the groups where they are. In other words, I group these 2 together and I group these 2 together, and we see what happens. Okay? So what we're doing as we group them together is we're actually looking for common factors. So within my first group, 2w cubed and negative 2w squared, we're going to look for their greatest common factor. So what is the biggest number, like numerical value, they have in common? 2. And then variable component, w squared. And we write what remains. So if I take 2w cubed and take out a 2w squared, I'm left with w. And the other one, I'm just left with a negative 1 because there's nothing, quote unquote, right? Division gives me a 1. Second piece. It is an addition sign, so I need an addition sign here. 3w and negative 3 have a 3 in common. And if I take that 3 out, I'm going to be left with w minus 1. Now, this is not by chance. It's intentional. If those don't match, your groups were wrong, or the problem doesn't factor by grouping. Right? They'll always match if it's been done with grouping properly and so forth, and that's how the correct way is to solve the problem. So now here's the kicker. If you look at all of this, and all of this, like it's actually each individually a term, what do they have in common? W minus 1. So I'm going to factor the w minus 1 out in front of the whole thing. And when I do, I'm left with those pieces. Right? When I factor w minus 1 out of 2w squared times w minus 1, I'm left with 2w squared. And likewise on the other piece, I'm left with 3. And then I'm done. And I hate to beat a dead horse, but how could I check if I wanted to make sure I did it right? Multiply back out, right? Yeah. Okay. So, same thing on the next one. I'm looking for groups because there's 4 terms. But something happens here intentionally because I chose the problem. That didn't happen before. What happens? Those groups don't work, right? There are occasionally going to be places where the groupings, just the way they're already situated, don't work. And the reason they don't work is because if you consider them, there's nothing they have in common, right? This has got nothing in it in common, right? ADY and W, nothing in common. So those are not good groups. So I'm just going to shuffle it to choose something different in my groups. And you have two options still. You can either do the outer and the inner. That might be a choice. Or you can do the first and third, second and fourth. So you pick whichever one works, and they might actually both work at that point. But actually the one that I've still got marked on my screen is the only one that works on this one. Okay? So on this example, the ordering didn't work originally. We had to shuffle them. So if I consider the ADY, and if you need to rewrite it so it's easier to see it in the order that we want now, you can do that. So as I consider the AD and Y and the D, now they actually have something in common, namely a D. And if I take out the D, I'm left with AY plus 1. On the next one, what do they have in common? Yeah, a negative W. And be a little careful when you do that because you need to take the negative out of both of the pieces. So this ends up being a positive in the middle. And then AY. Now, while they're not written in the same order, these are the same thing, right? AY plus 1 and 1 plus AY are the same. So we have factored correctly so far in factoring by grouping because we did, in fact, get the same binomial in the parentheses. And since they match, we can factor that out in front. So AY plus 1. And I'm left with the D and the negative W. So D minus W. And if you didn't want to write AY plus 1, you can write 1 plus AY. That doesn't matter. You can do that too. All right. So we're going to leave that right there with factoring by grouping. Have one more type of factoring that has a name that we're going to talk about. You ready? Okay, so we're going to talk about factoring trinomials. There are lots of ways to factor trinomials. I'm going to talk about two of them. There's at least one other that you may be familiar with. One of the ways that you may be familiar with is called slide and divide. Have you ever done slide and divide? Okay, a few of you have. If you know how to use slide and divide very well, you're welcome to use it, and I'm totally fine with that. I'm not teaching slide and divide. And the reason I'm not is because it is a little more hidden with what's going on. How does it work kind of thing. The way that I learned to factor was with trinomials is guess and check. So I'll talk about guess and check in a minute, and that's still the one that I tend to use the most, guess and check. Guess and check works really well when you have coefficients that are the number 1 in front of the x squared term. So guess and check would work fabulously on this particular problem. Fabulous. But when you don't have numbers that have a coefficient of 1, like the next two examples, it's not quite as clear and easy to do the guess and check. And you'll see that when I show you how that works. So I want to present to you another option that you may not have seen before. It's called the AC method. So here's the basic idea for it. To factor ax squared plus bx plus c, you find two integers whose product is a times c. Okay, so the product has to be this multiplied, the a and the c multiplied, and its sum is b. So it adds to a times c, and it multiplies to a times c, and it adds to b. You replace the b with those two numbers. So instead of it saying bx in the middle, it's going to have two other pieces that add together to give you b in the middle. And then you factor with grouping. Okay? So let me show you the AC method used on this one. It's definitely overkill for this problem. So as you look at this, you're going to be like, that was a lot of work for not a lot of gain. But it works better, again, when I get to the next slide, with that coefficient at the beginning when it's not a 1. Okay, so here's the way that it works. AC. So the number in front of the x squared is a. That's a 1. The number in front, at the end, c, is a 12. So a times c in this case is a 12. And the b in the middle is a 7. Okay? I need two numbers that multiply to 12 and add to 7. 3 and 4, right? My two numbers have to be 3 and 4. And to be honest, the reason that this method works nicely for the next slide is because it eliminates any other things that don't work. Okay? It will be the right numbers. If the two numbers multiply to 12 and they add to 7, they are the right ones. So what we do is we take this middle term that's the 7x and we rewrite it, so I still have the x squared, and it doesn't matter the order, as 3x plus 4x. And I leave my 12 written at the end. So I break the 7x into 3x plus 4x. Okay? And then I factor with grouping like we did on the previous slides. X squared and 3x have an x in common, leaving me with x plus 3. 4x and 12 have a 4 in common, leaving me with x plus 3. Of course, the x plus 3's match. That's the whole point of factoring by grouping, so I factor it out. And I'm left with x plus 4. Okay. Now, let me show you guess and check for this one because it works very nicely for guess and check. Guess and check says, well, we're just going to start out by writing two binomials down. And we're going to ask ourselves what two things have to multiply to give me x squared, and that's really easy. It's x and x. Then we look at the signs and we say, hey, there's a positive sign at the end. What that means is that my signs have to match. Positive times a positive is a positive, a negative times a negative is a positive. And because there's a positive in the middle, positive is what I want. So I have positive and positive. And then I say I need two numbers that multiply to 12 and add to 7, just like I did on the AC method a moment ago. And 3 and 4 come to the front very quickly. So this one works great with guess and check because there's not a lot of things to guess or to check. And of course, you can multiply it back out if you want to make sure you did it right. So let's see why guess and check is more complicated as we do the next two. 8's not as bad as 9. 9's worse, but 8's not as bad. So if I try guess and check, so let me do guess and check on this first, and then I'll show you the AC method. So with guess and check, I have to have two sets of parentheses, and I need two values that multiply to 3x squared. Well, I only have two choices. I only have one choice, the two values that work. I have x and 3x. There are no other ways I can do that, right? So that's not too bad. Now, if you take a look at something that wasn't prime, like 3 is, it's worse. If the number had said 4x, well, it could be, 4x squared, it could be 4x and x, or it could be 2x and 2x. Now I have two options that I have to guess, and pick one and check it. Signs. So I mentioned before the sign at the end tells me what to do. The sign at the end is negative. Well, the only way to get a negative is that one of them is positive and one of them is negative, and now I have to make a choice. Do I put the negative here and a positive here, or did I just do it backwards? I don't know for sure. I have to choose one and try it. So I'm not looking at my notes. I'm just randomly trying something. So it might work for us and it might not. We'll just have to try it out together. Yes?
Does it matter to the multiplication? It's going to all end up negative, right?
No, because that negative there at the middle won't apply to everything. This negative here, if it's here, like when it's written, will only apply to these two pieces, but it wouldn't make the x at the beginning negative. Yeah. So if the sign's wrong, like if we end up with something here, I might need to switch my signs. Like that's a possibility, a legit possibility that might happen. The number at the end is also prime, which actually is friendly too. It's 1 and 2. But unlike over here where I had 3 and 4 and it didn't matter where they went, the 1 and the 2 matter. And the reason is because the first pieces don't match. One of them's 3x and the other one is x. So we're going to randomly put them in there and see if it works. So I have 2 and 1. Okay, put a 2 and a 1 in there, in that order. And I have to check it to see if it's right. And what I really need to check is not the first term and not the last term. I know those are right. X times 3x is 3x squared. That's how I picked my numbers. Negative 1 and 2 is negative 2. That's how I picked my numbers, right? I don't need to check those. Those are going to be right. What I need to check is what happens when I do the inner and the outer terms. The inner term here is negative 3x. The outer term here is positive 2x. do those add to the positive 5 in the middle? They do not. So this is not the right combination of things. There's only two places where I had an option. I had an option where I put my negatives, and I had an option where I put the 1 and the 2, right? Likewise, you could say I had an option where I put the 1 and the x and the 3x, but I need to switch something. So I can switch the 1 and the 2, or I can switch the negative and the positive, and I can get all my options. If I just switch the negative and the positive, all it will do is it will change these signs. That's not achieving for me my goal that I want. So the only time the sign is the issue is if the answer is the right value but the wrong sign in the middle, and this one isn't. So what does that tell me? Well, it tells me that my 2 and my 1 are in the wrong spot. This one should be 2, and this one should be 1. And then we check again. So this is negative 6x now, and this one is positive 1x. What happened? The signs are now wrong, but that's an easy fix, because if the signs are now wrong, all I have to do is to change the signs here, and now they're right, and I get my 5x in the middle. Okay? And that's when their prime numbers are involved. What happens when they're not prime numbers involved? It's harder. So let me show you what guess and check looks like, not guess and check, I'm sorry, the AC method looks like on this one, because it does actually yield an easier elimination process for this one. So AC, well, the A and the C are the 3 and the negative 2. And 3 times negative 2 is negative 6. And my B value is 5. So I need two numbers that multiply to negative 6 and add to 5. Well, what would those be? Okay, so I need a 1 and a 6. Which one needs to be positive? Positive 6, negative 1. These are two numbers that multiply to 6, negative 6, excuse me, and add to 5, right? So what I do is I take what's given to me, 3x squared, and I replace the b term in the middle, that's the 5x, with those values. And again, it doesn't matter the order at all, and never will on these. So you can put negative x plus 6x, or you can put, negative 1x plus 6x, or plus 6x minus 1x, either way. And then we have a negative 2 on the end. And we will factor by grouping. So 3x squared minus x has an x in common, leaving me with 3x minus 1. 6x minus 2 has a 2 in common, leaving me with x minus 1. There's that, 3x minus 1, left my 3 out. So there's that 3x minus 1 in common, and there's that x plus 2 that's on the outsides. All right. The last example of these, on number 9, this type, harkens back to the idea that we need to be careful when we begin that we don't have common factors in everything before we start. Because if you look at this one, hopefully looked at it and you're like, hey, look, they're all even numbers. At least that. Or maybe you said, hey, look, they all have x's in them. And in fact, both of those things are true. So the first thing that we're actually going to do here is to take out a 2. A 2. I'm going to take out a negative as well, because I don't really want a negative at the very beginning of my factoring. That makes things very messy. So I'm going to take out a negative 2. And they all have an x in them, so I'm going to take out an x as well. So if I take negative 6x cubed and divide it by negative 2x, what am I left with? 3x squared. 2x squared in the middle leaves me with a negative, right now, x. Sorry, that was 3x squared, negative x. And at the end, I had 48x. So my sign will change as well. The 48 becomes a 24, and I'm done. 24 is like the worst possible number to show up to have to deal with factoring. You'll have no idea. How many things do you know that can multiply to give you 24? Quite a few, actually. 2 times 12, 3 times 4. What do I have else? 3 times 4. 3 times 8, 6 times 4. 1 times 24, that's actually an option too. And then you throw in the mix that the other number's a 3. And while you might think, well, the 3 is not so bad, it actually ends up being quite messy, just like the 3 did last time, because now it matters where you put, right, the 6 times 4. So we're going to do this one with an AC method only, because it actually is really hard to do this one with guess and check. So for the AC method, we're using this and this and this, right? So A and C are 3 and negative 24. Signs matter, so keep them. So this is actually negative 72. Thank you. And then my B value is negative 1. So I need 2 numbers that multiply to negative 72 and add to negative 1. Good. There's negative 9 and positive 8. Y'all good with that? Negative 9, positive 8. So over here, my negative 2x stays on the outside. And then I'm going to have negative 9x and positive 8x in whichever order you like, minus my 24. Okay, so I'm rewriting this negative x here in the middle with the negative 9x and the positive 8x, which is equal to what it was, just expressed differently. So I have negative 2x, and then these two have a 3x in common, leaving me with, I'm going to change this to be a bracket just to clarify, make sure we're all in the same spot. There's a 3x they have in common, and if I take that out, I'm left with x minus 3. The 8x and the 24 would have an 8 in common, leaving with x minus 3. So I have the negative 2x, the factor they have in common is x minus 3, and then the pieces they didn't have in common are 3x plus 8. All right, I have just a few more to show you. They're called other factoring in your book. Like there's these other factoring things. 10, 11, and 12. So let me run through them with you. And I'm not going to do the AC method on the ones where guess and check is easy because I don't feel the need. When guess and check works, it works great. If you take a look at this one, it's a trinomial, right? But it's not x squared, x, and plane, right? Like that's not what it is. Neither do they have things in common I can factor out, okay? But somehow it feels like it's kind of like the x squared and the x and then the constant. And it is. So this actually factors really nice by guess and check. But the kicker is that instead of writing just y and y here, because that would just give me y squared, I write y to the 4th and y to the 4th, because that gives me y to the 8th. The sign at the end is positive, which means both signs are the same. The sign in the middle is also positive, which means the same signs are positives. And then, much like with the AC method, but I only have to consider C because A at the beginning is 1. I need 2 numbers that multiply to 12 and add to 8. 2 and 6 or 6 and 2. And this is for sure and certain done because there's no sum of squares. Even if some of these had something squared, there's no sum of squares formulas, and these are both sums. So we're finished with it. And this is as good, if you will, as it gets with it factoring it. Oops, that's not what I meant to do. That's what I meant to do. Number 11, we have a common factor, right? What do they have in common? B squared, so we'll pull it out first. And after we do that, I have a to the 4th minus 16. So again, this isn't quite like a squared minus b squared, but it's awfully close. I do in fact have something squared minus something else squared. But what I have is I have a squared squared, and I have 4 squared. So, actually I was doing it before over here. The b squared stays in front, and then I will have a squared minus 4 and a squared. Actually, I'm going to put the plus 4 first. A squared plus 4 and a squared minus 4. Not because it matters exactly, but maybe you'll see in a second. Okay, is that good so far? But it's incomplete. And the reason it's incomplete is because there's still a difference of squares in that expression. right here. I can do it again. What's squared? Well, a is squared, and 2 is squared. And it's a difference, right? Like I still have the a squared here and the 2 squared here, but it's a sum. There's no sum of squares formula. There's only a difference of squares formula. So I can't utilize it and do anything differently in the middle term that I've got right now. So the b squared stays, the a squared plus 4 stays, but this a squared minus 4 has to alter itself and be a plus 2 and a minus 2 in some order. And at that point, I'm actually done. Okay, last example. It'll only take me a minute, so bear with me. 4 terms. What do we do when we have 4 terms? Grouping. So we're going to group. As we group, I have x cubed, and then it takes out x minus 2. And over here, I have an 8. And I'm taking out the negative with the 8, which will change the sign, so this is also x minus 2. Right, because I'm 16 divided by the negative 8 gives me negative 2. They have the x minus 2 in common, but I'm left with x cubed minus 8 on the other 2 pieces. Much like on the last problem, where I still had a difference of squares when I got to this point, this has a difference of cubes, doesn't it? So one of the things I want to leave you with as we finish this problem is that you always need to make sure that everything in your final answer is actually completely factored. This one isn't yet. So I have to do one more step, and I have to use the factoring formula for cubes. So that factoring formula is x, 2 cubed is 8, so this is 2. So x minus 2. I have to do the first term squared and the last term squared. I need the opposite sign, the middle 2 terms multiplied, so it's 2x. You can leave this as 4 squared at the end. Don't leave this as 4 squared at the end. We will write it as a 16. You can leave this, though, here if you wish. Or what you might actually see if you looked like in the back of the book on this one is that they might actually write this as x minus 2 because it's x minus 2 times x minus 2. And then x squared plus 2x plus 16. I don't care in the slightest if you do this as down down bottom. But I just want you to know if you see it, it's the same thing as you did before. Because it's just x minus 2 times x minus 2 representing the squared. All right, so homework for Tuesday. P4 and P5. But I will promise you that between Tuesday and Thursday next week, it will only be one section. Okay? One section between Tuesday and Thursday since we got through our 2 today. Have a great weekend, guys.